Good afternoon. I am Mauro Feliziani from University of L'Aquila, Italy. I will present EMC and EMF safety issues in near-field wireless power transfer systems. This presentation has been carried out in cooperation with my colleagues Tommaso Campi from L'Aquila University, Italy, Silvano Cruciani and Francesca Maradei from Sapienza University of Rome, Italy. This is the outline of my presentation. Introduction to near-field WPT systems, automotive WPT systems, EMC and EMF safety, WPT design, magnetic field calculation, numerical dosimetry, magnetic field mitigation, conducted emission, and conclusion. Near-field WPT systems. The near-field WPT technology is based on the Faraday law of induction to two magnetic resonant coils, the transmitting or primary coil and the receiving or secondary coil. Two couplet coils can be modeled by an equivalent circuit with two couplet inductors and some resistances to model the losses. Normally, the WPT technology is used at resonance, introducing two additional capacitors, C transmitter and C receiver. The WPT performance, I mean efficiency in transferred power, is greatly improved at resonance. Near-field WPT application. Wireless charging system will be widely used in the future for many applications. Several technologies are available for WPT systems, but we concentrate on magnetic resonant coupling. This is the most widely used technologies for near-field WPT systems. One of the key problems is the frequency selection, which depends on power, range, admissible bands. The most typical applications are in the frequency range between 10 kHz and 30 MHz. In this picture, you can see some application and correspondent frequency. There are biomedical devices, portable electronics, drones, light or duty vehicles, and heavy vehicles. In this slide, you can see automotive WPT application to charge the battery of an electrical vehicle. There are two different wireless charging, stationary with the vehicle stopped or dynamic with the vehicle in motion on an electrified road. Stationary wireless charging is almost ready to use technology, and there is some standards. The main standards are from ISO, IEC, and SAE. This last is very important because it fixes the operational frequency at 85 kHz, the power levels at 3.7, 7.7, 11, and 22 kilovolt amperes, and there are also 3 zeta classes about the separation between the primary and secondary coils. Also give some specifications about coil design. As regards dynamic wireless charging, this is a future technology and it will have a key role in the next generation of autonomous driving system. In this slide, you can see the architecture of a stationary WPT system. The battery charging takes place only when the vehicle is stationary. The transmitter is mounted on the ground in the ground assembly. The receiver is mounted in the vehicle. Typical installations are in parking areas, garage, charging areas, and so on. The pros are high efficiency, around 90% from AC to DC. The cons are that the vehicle must be stopped for a long time to fully recharge. In the picture, in the bottom of the page, you can see a WPT flow diagram starting from the AC grid. Then there is the ground assembly and the vehicle assembly. In this slide, you can see some converters, inverter. impedance matching network filters, and GA coil coupled with VA coils. They communicate wirelessly. In the second block, there is the vehicle assembly with some converters arriving to the battery. Now I'll give you some information about EMC and EMF safety in near-field WPT system. First, a near-field WPT system produces a certain level of electromagnetic interference, EMI, that can adversely affect the performance of nearby electrical electronic equipment by radiated and conducted emissions, giving rise to EMC, EMI issues, where the victims are the electronic devices. Second, the currents of the WPT coils produce significant magnetic fields in the environment that can induce adverse health effects, internal electric field and SAR, in the human body. So there are some electromagnetic field safety issues in which the victims are the humans. Please note that WPT systems must comply with EMC and EMF safety standards and regulations. EMF safety standards and regulation for near-field WPT systems. At international level, there are two main standards: ICNARP guidelines for limiting exposure to electromagnetic fields and IEEE standard C95.1 for safety levels with respect to human exposure to electromagnetic fields. There are mainly two kinds of exposures: general public or workers, known as a restricted environment in IEEE standard. The frequency range is from 0 Hz to 300 GHz. Dosimetrical quantities are the physical quantities inside the human body that can never be exceeded. They are known as basic restrictions in ICNIRP and as dosimetric reference levels in IEEE standard. They are given in terms of electric field or in terms of specific absorption rate, SAR. There are also some derived limits, which are known as reference levels in ICNIRP and exposure reference levels in IEEE standard. They are given in terms of electric field or magnetic field. In this slide, I give you some information about EMC standards for WPT systems. First of all, WPT systems are not yet fully standardized for EMC EMI. The main standardization bodies are I2R, IEC, CISPR, IETSI, CEFT, FCC, and some other national bodies. The main question is the WPT system an ISM or a short-range radio device? The limits are set mainly in radiated emission. The limits are very different each other among different standards, so the standardization process is ongoing. In this slide, you can see the spectrum management and the radiated emission limits in the frequency range between 9 kHz to 30 MHz. In yellow are highlighted the bands, the frequency band used by popular WPT systems: Everterrain, Automotive, QI, Airful, and so on. In the figure, you can see three curves corresponding to the limits of SAE, IC, and IETSI. How you can see, there are big differences between limits, and so the standardization process is ongoing. I also reported the electromagnetic field safety limits in terms of magnetic reference levels. WPT design. How to model a WPT system. In this picture, you can see a block diagram with voltage source, primary compensation, coupled coil system, secondary compensation, and load. The block diagram can be transformed in an equivalent electrical circuit with only analogical components. There are two coupled inductors, the compensation capacitors C1 and C2, while the voltage source block is modeled by Thevenin theorem, while the load is modeled by simple resistance at resonance. The most important circuit parameters are the current flowing in the coils, the input power at port 1, the output power at port 2, and efficiency. We adopt a circuit approach to evaluate the electrical performances of the WPT systems, while the field approach is used to extract the circuit lamped parameters, especially the inductances, and to solve the electromagnetic field equations. How to calculate the magnetic field emissions? We propose a three-step procedure. In the step 1, you have to use numerical analysis of the configuration under examination, for instance, a vehicle with WPT coils, to extract the circuit parameters of the WPT system equivalent circuit. Then you can analyze in step 2 the equivalent circuit, and by this solution you can obtain the currents flowing into the coils. These currents are used in step 3 as magnetic field sources to calculate the magnetic field distribution in the environment. Numerical solution of field equation. Magneto-quasi-static field equations are generally suitable to model near-field WPT systems, for instance, at the frequency of 85 kHz. The field equations can be solved in the frequency domain by numerical methods such as the finite element method. The main challenges in the field solution are, number one, modeling of a vehicle body shell made in steel or in aluminum. At 85 kHz, the penetration depth is small, therefore the conductive regions must be well discretized using a fine FEM mesh leading to a high number of unknowns. To overcome this issue, special numerical techniques such as transition boundary condition, impedance network boundary conditions, artificial material single layer method, etc. can be used in commercial software tools. If the body is in carbon fiber reinforced polymers, ad hoc models are needed because CFRP is anisotrope and highly penetrable. In this slide, I show you how it's possible to model the conductive layers in order to reduce the high number of unknowns in numerical calculations. In the first method, the impedance network boundary conditions, you can see a conductive layer embedded in a computational domain. By this method, the conductive layer is eliminated from the computational domain and replaced by boundaries. In these boundaries, the tangential field components are coupled, and they can be modeled by a two-port network, which is equivalent to a lossy transmission line. In the second method, known as artificial material single layer method, you can replace the traditional finite element discretization in which the conductive layer must be finely discretized. In the AMSL method, the conductive layer is discretized only by one finite element layer, in which the physical constants are artificial, and they are obtained by some mathematics. In this slide, you can see carbon fibers. Carbon fiber structures are given by a multiply structure, composed by many plies. In each ply, there are some conductive fibers, carbon fibers, embedded in a dielectric matrix. in the multiply structure, you can have high anisotropy. We perform some tests of shielding efficiency in which there is a coil exciting a carbon fiber panel. And we compare the results obtained by carbon fiber panel with aluminum. You can see the big differences between carbon fiber panel and aluminum shield. So we can observe a very good shielding performances of carbon fiber panel at 85 kilohertz. Now we come back to the main challenges in the field solution. Second point is modeling of WPT coils. You can see in this picture the automotive coils, GA coil and VA coils. You can see that there are the windings and also some ferrites and some conductive shields. And it's not easy to model accurately all these details in numerical tools. Another big problem is about Litz wires modeling. Litz wires are designed to reduce the skin effect and decrease the AC resistance by replacing the single wire by numerous insulated strands with diameter smaller than the penetration depth. Modeling Litz wires with a commercial software tool is not always possible. Then the resistance of the Litz wire is taken from datasheets. In this slide, we compare the magnetic field distribution obtained by three different body shell materials: carbon fiber body shell, steel body shell, and aluminum body shell. As you can see, in the carbon fiber body shell, the magnetic field penetrates inside the vehicles, while in steel and aluminum body shells there is not big penetration inside the cabin. This depends because carbon fiber body shell has a very good shielding at 85 kilohertz. In this slide, you can see the assessment of compliance with EMF safety regulations. First, exposure below reference levels ensures compliance with basic restrictions. Second, dosimetric analysis is requested whenever a reference level is exceeded to test compliance with the relevant basic restriction. To perform dosimetric analysis at low frequency, we propose a two-step calculation to reduce the computational cost. The main assumption is the presence of the human body does not modify the distribution of the magnetic field produced by the currents of the coils at 85 kHz. It is assumed that the reaction field produced by the induced currents are too small to modify the distribution of the incident magnetic field. So, at step 1, the magnetic field is calculated without considering the presence of the human body, which are quite transparent to the incident magnetic field. Second, the internal electric field is then calculated inside the human body, assuming as input the already calculated magnetic vector potential distribution. In this slide, I will present an example of the two-step calculation procedure of the internal electric field. In the first step of the procedure, the magnetic flux density is calculated in the whole computational domain without considering the presence of the human body. If the reference levels are exceeded, a dosimetric analysis is carried out in a reduced computational domain depicted by a dotted green line. In the second step, which is related to the dosimetric analysis, we calculated the internal electric field in a reduced computational domain. And we calculate the internal electric field, the current density, and the SAR inside the human. In this example, for instance, there is an exceedance of the basic restrictions of the electric field in the fits of the driver. Now we see the magnetic field mitigation. First of all, we have to consider that WPT coils are intentional sources of magnetic field. It means that there is a strong magnetic field in the environment. Second, the magnetic field mitigation can decrease the WPT performance. Now I'll show you the most popular mitigation techniques for reduction of the magnetic field produced by WPT coils. The number one is shielding, using magnetic material like ferrite panels or conductive materials, typically aluminum, or reactive or passive loops, or active shielding coils. Another possibility is to mitigate the source, reducing the amplitude of the currents or rearrangement of wires and current paths. Finally, it's possible also to modify the coil current distribution by a suitable WPT compensation. In this slide, we can see conductive and magnetic shielding. Conductive shielding is based on Faraday's law. Time-varying electromagnetic fields generate electromagnetic forces that give rise to eddy currents in conductive material, which are sources of reflected fields. The cons of the conductive shielding is that the field produced by the eddy currents can affect negatively the WPT operations. Magnetic shielding. The magnetic material provides a preferential path to the magnetic flux lines. The incident magnetic field is then not blocked but diverted into the magnetic materials. The cons is heavy, high-cost material, for instance, ferrite. Compensation coils are used to mitigate the magnetic field produced by WPT system. The idea of compensation coil is to introduce an additional coil. This coil produces a current which generates a magnetic field that can oppose to the incident one. In conclusion, we have a system of 3 coupled coils. There are 2 kinds of compensation coils, passive and active. In the passive coil, the current is generated by Faraday's law application when the coil is terminated on a capacitance. This is very important to obtain a magnetic field opposite to the incident one. In the active coil, the current in the additional coil is generated by independent voltage or current sources. Obviously, active coil is more complex than passive coil. In this slide, you can see an example of active shielding applied to WPT coils. In this configuration is reported the GA coil and the VA coil according to the SAE specifications. There are also 4 additional coils. These coils are active. It means that they are independent powered. The configuration of each active coil is reported in this part of the figure. As you can see, there are 4 active coils and 2 WPT coils for a total of 6 coils. So the equivalent circuit is based on 6 coupled coils. The goal of the active shielding is to minimize the field beside the electric vehicle. In this slide, you can see the results obtained by the active shielding technique. Here, there is a measurement plane. This is the magnetic field map on this plane when the active shield is off, and the other picture is the magnetic field distribution when the active shield is on. You can see a significant reduction of the magnetic field. This reduction can be seen also on this line 1, in which you can see the field without active shielding and with active shielding. In this slide is reported also the CNIRP 2010 reference level. I'll show you now how it's possible to apply active shielding to dynamic WPT systems. This is the coil configuration, in which there is a GA coil on the road, an active coil parallel to the GA coil on the road, and a VA coil on board of vehicle. The coil configuration is reported in this part of the slide, and the data are derived from European Union Fabric project. The magnetic field minimization has been carried out to minimize the field in this volume depicted in green. Then we have performed the magnetic field calculation in this measurement plane without active shielding and with active shielding. And you can see a strong reduction of the magnetic field when active coil is on. Magnetic field mitigation can be obtained by suitable compensation network. In this picture, you can see an equivalent circuit of a WPT system, assuming a series compensation network. It means that the capacitances are in series connected to the inductances. Adopting another network compensation based on LCC compensation, it is possible to modify the distribution of the current flowing into GA coil and into VA coil. LCC compensation is obtained by introducing a series inductance and a shunt capacitance to the previous circuit for both primary and secondary sides. In this picture, the results obtained using LCC compensation to mitigate the magnetic fields are provided. We are considering a vehicle during wireless charging, and we would like to mitigate the field on this measurement plane. In this picture is the field obtained using SS compensation, series compensation, while in the other figures we have adopted LCC compensation. As you can see, there is a big decrease of the magnetic field using LCC compensation. Another significant EMC problem is related to conducted emissions. In this slide, you can see in the blue curves the voltage at a point upstream of the converters, close to the AC grid. You can see that the peaks are higher than the limit given by CISPR 25. Adopting an EMI filter is possible to reduce the peaks of the voltage. You should also note that adopting a different compensation, for instance LCC compensation, is possible to reduce the harmonic content of the voltage. Obviously, introducing a filter, this content is greatly reduced. Conclusions. EMC and EMF safety are very important aspects for the widespread use of the WPT systems. EMF safety standardization has been recently established, while EMC standardization of WPT systems is ongoing. Magnetic field levels can exceed ICNIRP reference levels in some WPT configurations. Therefore, dosimetric analysis is often necessary. Conducted and radiated emissions of WPT systems can be a critical problem. Accurate prediction of magnetic fields requires complex numerical models. And finally, mitigation techniques of the magnetic field, such as active shielding coils or LCC compensation, are very important to comply with the EMC and the EMF safety standards and regulations. In the following 2 slides are reported some references of our research team. Thank you for your attention. For any question, please contact me in chat or at my email address. Thank you.